Thank you, Luke. And I think thanks again to Luke for all the effort that he puts into organising these tutorials and this UKCA theory and practice course. Fairly last minute, I was kind of asked to do something, and in years gone by, in previous versions of this course, we've sort of ran interactive sessions on the Friday morning, and I hope we can still kind of be interactive, even though we're going to talk about model evaluation, which I don't know. It's one of these things that it's not a necessary evil. It's necessary. It's incredibly necessary, but because it involves statistics, I generally don't like it that much. And I've tried to throw some humour in, and you may or may not find anything that I say funny. And as an opening gambit, there's this comic strip from XKCD, which I really recommend you looking at when you get to that sort of time on a Friday afternoon where, you know, the pub's open, yeah, but you really should be in work. So why not just look at XKCD for some inspiration? And you'll see funny little quick bits like this about statistics. And so with model evaluation, I think the challenge is, well, the biggest challenge that we have is we want to understand how and why the atmosphere works. And the problem that we have is that the atmosphere is a hideously complex beast. So to tackle this challenge of understanding how and why the atmosphere works, I think there are three solutions. And often when we talk about atmospheric science, we talk about a three-pronged approach to atmospheric science. So one of those solutions to understanding how and why the atmosphere works could be to observe it, to look at the atmosphere in its natural state, or the atmosphere as it is. So we kind of call that field observations or observational science. We can also then try and simulate the processes that happen in the atmosphere in the laboratory. And for those of you who are kind of interested in atmospheric chemistry, then we can kind of define very controlled conditions to study individual reactions one at a time. And those laboratory studies, I mean, can also be extended to looking at fluids and the fluid dynamics of the atmosphere, again, controlled situation. Or we can develop mathematical representations and try and model the atmosphere. And that's basically what you are all here doing, right? You're all using this hideously complex model, UKCA, to try and understand just how and why atmospheric chemistry-climate interactions happen. And I think that's great. But I also think it's really important that we don't stay in this silo of being modelers, that we also are aware about the fact that the best solution really is a combination of solutions. And so in model evaluation, we're really trying to confront our model with these observations of the atmosphere and with information from laboratory studies. But I think that the first bit, before we get on to model evaluation, is really just the model of a model. And really that all starts with a question of what are you interested in understanding? So what is the question of interest? And I just thought maybe we could do a quick poll of what people are interested in, what questions people have. So please do, as I'm going to pick on people, tell me, starting from the back, and I'll pick on Scott to begin with. Tell us what you're interested in, Scott. Thanks, Alex. I did ask you to come.
Yeah, I should set myself up for this.
Yeah.
Okay, how about oxidative capacity of the atmosphere?
Oxidate.
And how that feeds into methane lifetime?
Yeah. That's a brilliant question. Lifetimes, and let's just generalize that to short-lived climate forces. Have you come across this term before, SLCFs, people? No. So short-lived climate forces are, as Ron Sill says, you know, is exactly what it is. lifetimes of less than a few decades, and they influence climate. So things like methane, black carbon are some of the the poster childs of short-lived climate forces. Okay, so oxidizing capacity, lifetimes of SLCFs. That is a very important question. What other questions have people got? Let's see, going around the room. So, Alison.
The effect of volcanic aerosols on stratospheric ozone?
Volcanic aerosols on. These are good. These are very relevant to UKCA as well. These are good questions. Not, how do I get rich? UKCA won't help you get rich.
Also, how do I get rich?
Okay, as a sub question, we'll leave that one for later. Yeah.
Effect of biomass burning aerosols on total cloud cover.
Okay, let's say aerosol cloud interactions as a more yeah. Okay, and let's get one more volunteer. One of the questions that they're interested in. Anyone got something which is a bit more out there? Whether there's life on Mars? No. Air quality? Yeah. Okay, let's put something like air pollution and human health. I mean, and it really doesn't matter. The key point is that you need to start with a really defined question when we embark on this process of modelling, right? So once we have our question, so let's take aerosol cloud interactions. I think that's a really interesting question. The next step is to develop as simplified as possible a representation of the processes to be solved. So, I think there are more than two schools of thought here, whether or not you go and throw everything you know about this phenomenon and try and encode that mathematically and use that to develop a model and see what happens, or whether you start very simple and start very basic. And I mean, I think it's up to you really how you approach that. If we think about UKCA, so I don't think anybody would say, I want to look at aerosol cloud interactions on Monday and then on Friday have written how many, is it 100,000 lines of code?
UK says 100,000, yeah.
100,000 lines of code, which is UKCA, to tackle that question. I think you would start with a much simpler set of equations to solve, to see what you can do to begin with. And possibly for oxidizing capacity and lifetimes, you might start with just solving the continuity equations for the gases that you're interested in, and it can be as simple as this minus other terms. So we could solve that in an Excel spreadsheet. We could write a piece of Python code to solve that. We can actually, solve these equations and write nature papers to understand how the atmospheric methane budget is affected by changes in oxidants. It doesn't really matter. I think complexity is an important aspect of modelling, but the question is always the most important bit to get us going. But then at some point we do need to determine whether or not our model is any good, and that is where the process of model evaluation comes in. And a key aspect of that is determining which metrics and diagnostics to evaluate our model against, and to decide what sort of observations or what sort of data should we compare our model predictions with. And you can see the way that I've written this as an iterative loop. You don't just evaluate your model and that's it. You evaluate your model, and in that process you improve your model. And if you think about weather forecast models, I mean, that's the bread and butter of what happens in places like the Met Office and ECMWF. People are constantly evaluating the model performance and improving the model based on that process. And then eventually we get to a validated model, and then we can use that to do the really cool things like make predictions of how air pollution is going to affect health in the future, or volcanic aerosols are going to affect stratospheric ozone. And so if we kind of just focus maybe on this aerosol cloud interactions, what sort of metrics and diagnostics do we think we might want to use to evaluate whether our model captures that process?
Absorption coefficient of the aerosol?
Yep. So the, should we say aerosol properties? Are we able to simulate the aerosol properties? Are we able to observe those aerosol properties as well? So how do we best observe those aerosol properties? Is that ground-based? So is that with aircraft? Is that with satellite data? How are we going to formulate this model? Are we going to just have, depending on how we can observe the system determines what sort of modeling framework we might want. If it's a system that can only really be observed in situ, we might need to have the ability to constrain other parts of our model, such as temperature or humidity or things like that, so that we can really minimize errors coming into this system, which are not to do with the representation, that simplified mathematical representation that we're trying to understand and evaluate. And so, and that's a key thing, sort of not only the diagnostics, but then also metrics. So what sort of metrics might we consider to evaluate our model? What about you, Luke? What's your favourite metric?
Depends on what I'm looking at.
Yeah, I think that's a good answer. I think common things that we might be interested in is the error, or the bias between the model field and the observations. We might also be interested in the correlation. And model evaluation often looks a bit like a beauty pageant. So if you think about things like CMIP5, this coupled model into comparison project, you often see models compared to observations, and the models which agree best with the observations are kind of the ones that everyone believes in. And that's part of this process, right? But model evaluation is more than just a beauty contest, as I think we'll go into. So how do we know if our model is right for the right reasons? So I think this is an interesting question. And often when you have an interesting question, the first thing you do is Google it. And if you do Google this question, the answer is apparently Nickelback's album, All the Right Reasons. I don't know if anyone can remember Nickelback, any of the hit tracks on this album. Rockstar? Yeah, we all want to be a rock star. Well, and if you stick in the climate modelling world, you probably won't be a rock star. But if we stick on the theme of model evaluation, how do we know if our model is right for the right reasons? I think this is the prime question when it comes to evaluation. We can get a good agreement with observations and be fundamentally wrong. Our model can look good. Our model can look beautiful, but actually be fundamentally flawed. So increasingly, there's a movement to look beyond evaluating, for example, the aerosol absorption coefficient or the surface temperature, but to dig into the processes. And actually, maybe aerosol absorption coefficients are a good example of being more process-oriented. So when you see the phrase process-oriented model evaluation. That's kind of the pinnacle of where we're going to or where we're at, depending who you speak to. What we can compare models against generally, as I've said, are things like real observations made in the atmosphere or in the laboratory. Other models, so model into comparison exercises are incredibly useful. I kind of touched on CMIP, so the next phase of the coupled model into comparison, CMIP 6, is just about kicked off, or it has kicked off. And not only is that going to include more modelling centres than ever before, so I think there's going to be the first African-led contribution to CMIP in CMIP 6. It's going to produce a lot of data. So the sort of the data output from the CMIP 3 looked something like this. CMIP 5 looked like this, and CMIP 6 looks a bit like this. It's petabytes of data, model data, and within those petabytes of model data, there will be lots of people who start to do this beauty contest evaluation of, do these models look the same? Do they look good against observations? And undoubtedly, one of the kind of the nicest products to evaluate gridded model data against are reanalyses products. And so centres like ECMWF produce these beautiful reanalyses of atmospheric prognostic variables, which we can compare models to. What's nice is, having a standard framework to produce these reanalyses means that we can look also at historical data, not just sort of data from yesterday or today. And ECMWF have just released their newest reanalyses product, ERA 5, and this is going to be again like drinking from a fire hydrant in terms of the amount of data available. But also it will provide really unique opportunities in terms of evaluating models as it has a coherent formulation of doing this reanalysis. And what reanalysis means is you use observations and you use mathematical techniques to enforce models to match those observations in a very nice sort of framework. So it gives us the best confidence of what the atmospheric state looks like and allows us to do some really nice evaluation. And when we talk about evaluation, I think evaluation really has 4 components. And the first of those is model calibration. And so that would be that first step. So if we think back to that flow chart of making a model, the first time you put your parameterization together and you test it, well, there are lots of values for parameters. You make an objective decision on Monday that the rate constant should be this value, and you plug it in to your model. You then evaluate your model against some observations or other model data, and then you can basically, if you have parameters that have some uncertainty, you can start the process of modifying the values that those parameters take. And you can do this manually, so sort of one at a time, where you probably have a good idea about which parameters are driving the uncertainty in your system or driving the system forward, or automated. And so we'll touch on perturbed parameter ensembles, which is a sort of a nice technique for doing this. So we calibrate our model against a set of data. We then verify our model. So we quantify the predictive capability of our model, again, comparing to observations. So for simple models and for simple code, the sort of stuff that you can write yourself in a Python script. Verification may also just include verifying the logic in the model. There are actually an increasing number of tools that can do some sort of code logic verification. I don't know if those sorts of tools are used in UKCA, but they are incredibly useful. It's very easy with hundreds of thousands of lines of code to make some assumptions which might be logically wrong about inputs and outputs passing through subroutines. I think, is there a guy in Cambridge who sort of does this logic testing? Yeah. So and there are people that actively work in that field, and it's an important field, but it is difficult to interface large codes with those sorts of checkers. In terms of model verification, I mean it's incredibly important that the observations you use to verify your model are not the observations that you use to calibrate your model. You're gonna have false confidence if you're using the same observational data set to tune your model and then say, oh look, I tuned my model and now it looks great. Huzzah. And the nice thing about observations are I don't think we're at a state where we've over-exhausted the observational database. I think all modeling groups underutilize observations. Model validation then is the process which determines whether or not, having verified our model against observations, we have a valid model to make predictions with. And so I like that quote, all models are wrong, some models are useful. And I guess a question to you guys is, can we validate a model like UKCA? And I'd appreciate what you think. So can we ever say UKCA is a validated model?
For some purposes, yes. For all purposes, probably not.
Yes, and so I think exactly it kind of comes to that question. What is the question? For what purpose are we using UKCA? And we might actually, refine that to being able to model changes in the oxidative capacity over annual scales. So we might think that actually it's also impossible to validate changes in oxidative capacity at the global level on diurnal scales because there aren't observations. We can't do it. We don't have any way to validate our model. And so I think, again, just think about that question that's driving the reason that you're using the model in the first place as to how far you can go with this important step of validating your model. You often see model verification and validation used in the literature synonymously. Just be aware that, I think formally they do mean two distinct and different things. So the last bit, which I think is increasingly important with complex models, is sensitivity analysis. And so this is that process where we might be interested in looking at the response of our model to a perturbation. And that could be in the inputs to the model or to the parameters inside the model. And when we change the parameters, one approach is this perturbed parameter ensemble, and we'll touch on that. But in terms of inputs, sometimes we have opportunities. So I think in 2014, have we got any volcanology experts? Hularan, which I probably can't say it right, was an Icelandic volcano, erupted kind of continuously, and it emitted the same amount of sulfur as I think all of Europe and North America, something like that. A huge amount of sulfur was coming out. And so you had this wonderful natural experiment to look at what happens when you pump tons of SO2 into the atmosphere. And so in terms of modeling, you then have the results of a sensitivity analysis of what happens if I pump loads of SO2 into my model. Does my model simulate these aerosol cloud interactions that I'm really interested in correctly? And I mean, other examples might be El Niños or heat waves or things like that. And so, again, just kind of look to the real world to see if there are opportunities to perform sensitivity analysis. And so these four important steps for model evaluation are calibration, verification, validation, and sensitivity analysis. And we have this formal set of definitions, but we also require some objective measures of goodness of fit. And so these are these metrics that we talked about in terms of error, bias, correlation. We've sort of touched on what we're comparing against, and again, I think this is an incredibly important question related to our objective. Are we going to be comparing against integral quantities from remote sensing or satellite? Is the process that we're looking at happening at an hourly or high time frequency? So do we need to look at hourly or high time frequency data? Are we actually able to just look at monthly or global averages? In terms of those metrics, there are many metrics to determine performance, and I've got a couple that we'll kind of go through, which are the common ones. Software like R and Python, I think they're really nice tools because lots of people who are interested in evaluating models use software like R and Python, and have made it possible to use some very high level or very sophisticated statistical functions very easily. So much so that you don't even have to think about doing a certain statistical test. And I mean, for those of you who kind of read Nature sort of opinion pieces, one of the most maligned statistical measures, I think, is the p-test, which people often incorrectly use. So again, I think it's a case of, rather than just trying to impress your colleagues by showing the significance of your results, think about what you're doing. Think about whether you really understand the metrics that you're trying to use to quantify your model performance. In terms of measures for bias and error, there are a range, so I just thought it was worth going through them. So mean bias, mean error, where we take the absolute value of the model predictions minus the observations, root mean square error, and just to kind of go through how straightforward it is to kind of code these sorts of things. Does anyone like R? Is anyone an R user? No, it's really the best. I don't have shares in it yet. I'm trying very hard to get a share in the company, but I think basically from next year all UKCA will be done in R. No, of course not. R is incredibly easy to get going, honestly, but for certain big data applications, R is incredibly slow, which is a bit paradoxical because it was designed for big data analysis and fast analysis. So a very quick R script, and just as in Python, which probably lots of you use, we have some low-level functions that come as part of the software, and then we can make use of libraries of functions. And so there is this nice NCDF4 library to read NetCDF data. And so in this small script, I'm loading in some of the UKCA CCMI RefC2 results, and this is Ensemble Member 1, Surface Ozone 1980 to 2010. So I open that file and I then extract the ozone tracer, and we'll kind of touch a little bit about converting PP to netcdf data. The netcdf variable name for ozone in this file is tracer1, and so I then just kind of go through, extract the time, and then what I wanted to just show you was how we can then write some simple functions, and this is, I'm sure, very similar in Python. It probably just looks a lot neater in Python. So we create a function called the mean bias, which requires us to have model and obs, and we say that function is the mean of the model minus the obs, mean error, etc., etc., and then we should be able to run this somehow. Oh, no. And this is churning through, and obviously you're very impressed with how quickly this all worked. And we've also plotted our two different data sets that we're comparing. So we're comparing the first 12 months of this ozone data to the next 12 months, and you can see that actually they're quite well correlated, as they probably should be. And then what we were able to do was print out a bunch of error measures for these two 12-month data sets. And so we have here the fourth one, 1, 2, 3, 4, the normalized mean bias, so the percentage bias, so 0.72% bias between these 2 years of ozone data. What does that mean? I don't really know. It was just to show you that it's quite easy, and hopefully, even though that took quite a while, you all are now convinced that you should ditch Python and use R for everything. I mean, Alison, you did want to get rich, right? And so a lot of economic and stock modelers use R, so maybe, maybe that's a good incentive. Okay, so there are just bags of different measures. I think it's important to kind of be aware about them. Normalized mean bias error, so we divide through by the sum of the observations there. Normalized mean error, fractional error. This is a bit dry. I won't go on this too much. The correlation coefficient is now, so this is a unitless measure, a unitless metric, and often that's kind of being used to tell us about to some extent the skill of our model in forecasting these or predicting these observations. So what's that relationship between the mean states of these model and observations? Index of agreement, coefficient of variation. These are all really good. So mean absolute error is just this straightforward measure of how far away our model and simulation was from our observations. It takes that again, so it takes the modulus of the absolute error, and so it's always positive. Then we have that mean squared error. It's a measure of both the bias and the variance of the model. So the variance of the model, the variance is the expectation of the squared deviation of a random variable from its mean. And so it measures the spread from the average. And so again, it kind of comes back to that question of what quantities are we looking at as to whether or not these are going to be good metrics for deciding model performance. If we're only interested in one-off events, so extreme events, then possibly this is going to give us false confidence in our ability to model those extreme events. This wouldn't be a particularly great metric for that. So, and this is sort of bread and butter stuff, and you can go back to papers, the very, very earliest atmospheric chemistry modeling papers talk about measuring error in these sorts of ways. And I just wanted to touch on some newer approaches to model evaluation. And really, a lot of this work comes from a group based out at the JRC in Ispra in Italy. So that's the Joint Research Commission or Council. And they published 2 papers in ACP. You can probably see the references in your printout. And they talk about error apportionment, which I think is really what we want to do. We can quantify that we have error, but really we want to apportion where that error comes from. We want process-based understanding of why our model doesn't look like the observations. And this is something that these guys have been trying to do in the context of an air quality modeling into comparison exercise. So that exercise is called ACME, and it's an international model into comparison exercise that looks at model simulations for Europe and North America. And Salazzo and Galmarini suggest that what we can use are metrics to relate the skill of the model, and so they kind of propose using this minimum mean square error and go through how this is related to the accuracy through the bias, the precision of the model through the variance, and the associativity between the model and the observations, and that's through this unexplained portion through the correlation coefficient R. And I think this is really nice. So they've kind of gone through and they articulate much more clearly than I can why these metrics are very nice for model evaluation to understand errors. Some pictures which aren't in your notes, sorry, show a breakdown of these different components of the error. So the bias, the variance, the minimum mean square error for ozone. And what we have on the bottom are the different models. And this is for Europe, continental-wide, in the peak ozone season, May to September, and basically split into different time domains. And so if we just kind of forget these first 3 panels and just focus on this long-term time domain, then we can see that actually for some models we can clearly identify that bias in the model in ozone is contributing most to the error. Now we don't emit ozone, so it's not a simple case of then going into the model and reducing the ozone emissions, but this can be extended, and in the notes I think I show more examples of how this can be extended to understand the processes a bit better. I'll skip that. A key part of Salazzo and Galmarini's work is that spectral decomposition. And so spectral decomposition isn't new. In fact, I mean, it's a technique widely used in aspects of atmospheric science, but just not so much in the evaluation of atmospheric composition. Here we've got a comparison of UKCA dynamical properties, courtesy of David Wade. And so on the right panel, we have the quasi-biennial oscillation in observations and in the model. And in the left panel, we have the ENSO 3.1 index. Again, the darker colors being the model and the duller colors being the observations. And so what we have on the x-axis is the frequency, so in inverse years, and then the power spectrum of that associated with those frequencies. And so what you can see is that actually our model very, very nicely captures the QBO. So the QBO is this shift in winds in the upper atmosphere that happens, as it says, quasi-biennially. So we have the right frequency, the time frequency for that is right, but somehow we have a slightly lower amplitude spectrum there. For ENSO, it's a bit harder to see, but and we don't have a quantitative metric like the bias or anything plotted here, but the broad features are being well reproduced, between the model and the observations. And I should say that in this case, the model is a fully coupled ocean atmosphere model, so it's not that it's just being forced by the observed sea surface temperatures. It's that the atmosphere ocean system is producing an El Nino spectrum, which is similar to those observations. And so in the context of ozone, what Galmarini and Sollazzo do is decompose this full time series of ozone into a long-term component, a synoptic component, a diurnal component, and an intraday component. And there are different ways to do these sorts of spectral decompositions. So you might have done Fourier transforms before in physics, or fast Fourier transforms. Least squares spectral analysis and the Lomb-Scargill periodogram are other techniques to kind of do this, a similar thing. Sollazzo and Galmarini make use of an algorithm called the Kolmogorov-Zubenko filter, which effectively allows them to extract these 4 different characteristic spectra from the signal. And just to kind of show you, if we take a long time series, this is several years of ozone observations in black and modeled ozone in red. Effectively what we're doing is trying to decompose this noisy signal into something that has in this case here we're doing a harmonic analysis, so we're looking at the first harmonic, the second, the third, the fourth, and we're actually trying to fit these data to these different harmonics. And so this is work by Bardello and Evans, and the reference for this work is kind of here. And I think they've done a really nice job of showing how we can use these Lomb-Scargill periodograms to evaluate ozone. So before I'd shown you the use of these sort of spectral analyses to look at meteorological or climatological features. Here, I think they do a really nice job showing that a model is able to reproduce the features in the power spectrum of something like ozone. And so what we have is characteristic features on that sort of annual cycle, that semi-annual cycle, and then when we get down to the higher periods, we start to see the daily cycle. And ideally, what we'd want to be able to do is to break down the error associated with these different periods and say, is the majority of our error in the seasonal cycle, in the long-term component of the ozone? Or actually, do we have more error in the diurnal component of ozone? So do we produce and lose too much ozone through fast photochemistry? Is it transport of ozone from long distances, which is causing error in our model? And that's the whole hope of this sort of model evaluation. I'll just sort of skip through to looking at something like CO. So carbon monoxide contributes to the formation of ozone, and so in their more recent work, Sollazzo et al. Have decided to do a more regional approach to looking at the model results in Europe, and you can see these circles represent the sites for observations that they're looking at. And you can see, so they're looking at hundreds of observations for each region, and then looking at the full time series in the top panel, the diurnal time series, the long term, and the synoptic. And what you see for all of these different models shown at the bottom, there's very little difference between them. And that actually the root mean square error now, which is the sort of the bias, that the error that they're using to evaluate the models, is most probably attributable to the emissions of carbon monoxide rather than anything else. So these are regional models, and so one question is always, are the inputs, your boundary conditions affecting the simulation? But they're able to kind of disaggregate that and say, no, the main problem with modelling CO in these regions is actually the emission inventories themselves. That's not a huge surprise. If anyone who sort of works with emission inventories, I think you have to take those emission inventories data with some critical skepticism. It's very, very difficult to make very accurate emission inventories. It's a really tough job, and there are big errors, and so we must be critical of those emission inventories. And this framework allows us to say, well, it's not chemistry. The bias doesn't show a signal which is stronger at the diurnal level. The strongest component of the bias is at the long-term level. So we can kind of attribute that bias then to the emissions. For NO2, there's much more model dependence now on the bias. So different models are having different diurnal error. And also in the long term, there's a lot more model dependence, but the majority of the error is really composed in the longer term and full time series. And so they conclude that the bias is the main contributor to the NO2 error and stems from this model under prediction of the observed concentrations during the year. And that's probably caused by a combination of factors, with emission estimates or the emissions being input being a likely a source. And actually, I mean, that's something that there's been quite a lot of literature more recently looking at the NOx sort of VW emission scandal as kind of highlighted a lot of misreporting of NO2 and NOx data in emission data sets. So I think this is a really nice way to do model evaluation, and this is certainly, you know, the most recent work that I've seen in this field. Was it a success? So I've just cut and pasted really the conclusions of their paper, and I think broadly, I won't just read it all out for you. Broadly speaking, it was a failure to actually quantify the processes causing the error in the model. It's a great step forward, but it's still not got us in a position where using this methodology allows you to unambiguously determine what the sources of error are in your model. So I think that's really compelling, because I think that says that, you know, there's an opportunity there for people like yourselves to really get involved in and to make a big impact in this field. As models are getting more and more complicated, I think model evaluation is only going to get more and more important. So we've kind of now gone over metrics and approaches to model evaluation. I just thought as well, it's kind of really important to contrast the model picture and the reality picture. And so one of these images actually shows a Turner-nominated art piece which sold for £150,000. Whoever went to see it? Did anybody actually go and see? No. I've not been to Legoland either. But I think it's really, it's really interesting. This is exactly, I think, the sort of picture that UKCA puts out, and this is the sort of the detail of the real atmosphere. Clearly, they both look like beds. They both seem to have the right dimensional aspect ratios to the components which are in the bedrooms, but one is a bed and one is a model. And let's never forget that. Let's never think that our model really is reality. We are just Lego builders. So I said I'd talk about perturbed parameter ensembles, and there are a large number of studies which are increasingly using this approach to evaluate model sensitivities. I picked on this one because I think it's really quite interesting. So this is a paper which looks at a perturbed parameter model ensemble to investigate the initial sulfur mass emission from Mount Pinatubo. So it's that problem. So the question was, can we constrain the initial mass of SO2 injected from Mount Pinatubo? We have observations and we have models, so how can we go about and constrain this important problem? I guess there are a number of different approaches, but effectively these guys decided to look at a bunch of different SO2 injection profiles, so injecting SO2 at different parts of the atmosphere, and then came up with a number of different metrics to determine whether or not the different simulations they ran gave a better agreement to the observations that they had available. And so what observations they had available were the microwave limb sounding SO2 observations. So these are satellite-based SO2 observations. They had optical particle counting observations as well, and more satellite observations. So 3 different data sets to give you sort of independent verification. I mean, the other thing is, in terms of thinking about how these 3 different observations observe the Pinatubo plume, they are looking at different things. It's not 3 independent data sets looking at the total SO2 column, which actually might also be very useful. What if you just get a good agreement because actually there's a bias in some of the observations? I mean, it's important to remember that observations can have biases too. But I think what's interesting is that they kind of ran a whole number of simulations and calculated these metrics and measures of success and averaged them, and then said that overall the model simulation that gave the best average of these different error measures was the best simulation. Which I think is an interesting way to go about doing this. And you can see that maybe visually, so this is the latitude time evolution of the Pinatubo column. And so we've kind of got increasing amounts. I think this is probably sulfuric acid aerosol mass. And increasingly red, dark colours are where we have higher concentrations, lighter colours, lower concentrations. And these are the observations up here. And these crosses are where they didn't have any observations, but they've just filled them in. And so basically saying, don't focus too much on these areas where the crosses are. And so we can kind of see, by eye, that there are large differences between these different simulations. But again, we need to go beyond just looking by eye. We want to quantify numerically how these different simulations compare and arrive at an unambiguous determination of which input parameters lead to the best simulation. And so a step further is going to emulation of models to quantify sensitivity to uncertain parameters. And so this is really nice work done in Leeds by Lindsay Lee. And actually, Lindsay's here in Cambridge at the Isaac Newton Institute, co-hosting a series of workshops on uncertainty quantification in complex models. And this is a huge area of active research, and I think this is some really nice applications of uncertainty quantification to environmental sort of models. All we need to know at a high level is that an emulator is a model of a simulator. And so UKCA is a chemistry climate simulator. It has equations, prognostic equations, which it solves to simulate the evolution of the composition climate system. And if we run enough experiments with UKCA, we can evaluate the output of the model for different perturbations, different inputs, and we can statistically map the results of the model simulations to effectively generate a model of the model. And that's what the emulator is. The emulator is a statistical model of your model. And what's nice is then you don't have to run your complex simulator anymore. So you now have a very cheap to run tool to tell you about how, if you were to change such a coefficient, it would affect the results of your model. And not only the deterministic result of your model, so often you run the model and you only get one answer, but this would tell you what the probability of a change would be. So it gives you a PDF of the response of an input. And so I think increasingly this is what we need to use when going through that process of model calibration. The sort of the one at a time model calibration is incredibly tough to do when we have lots of parameters in the model, and so this sort of perturbed parameter ensemble model emulation process, I think, is really the way forward. And effectively, I think it's the way that the group that Lindsay works with in Leeds, who are developing GLOMAP, have made a hell of a lot of progress. What this figure here compares is some work by Dom Spracklin in Leeds, looking at one at a time simulations to try and understand aerosols. And this was really great work. We mustn't forget that this was really great work. But we compare these one at a time simulations to the simulations that Lindsay performed with GLOMAP to show you basically how experimental design means that you can fill the parameter space much more efficiently by doing simultaneous perturbed parameter simulations rather than one at a time simulations. And the benefit of perturbing lots of parameters at the same time is you can start to see how interaction effects between the parameters can influence the results. If you just change one parameter at a time, you don't tend to get those interaction effects. And for some parameters, those interaction effects, which are shown in green, are important. And so here we have a bunch of parameters in GLOMAP, the SO2 emissions, the oxidation diameter, the accumulation coefficient. And Lindsay was able to contrast how the percentage of CCN variance explained was through the main effects of changing the parameter and through the interaction of changing all of the parameters. And so you see that actually in this rural location, there's much more of an influence of interactions than in this urban location where you kind of see these main effects cropping up. And I think an even nicer way to extend this then would be to take the Sollazzo and Galmarini time sort of space analysis and error decomposition analysis, and combining these approaches, I think, is what we should be looking to do with UKCA. And that's about it really for the model evaluation sort of theory side of things. And I think this, there are certain quotes which really stand out, and I think this is one which I really like when it comes to models from Einstein. Everything should be made as simple as possible, but not simpler. And I think clearly Einstein never used Stash, because anyone who's used Stash would say it can be made simpler and it should be made simpler. So for the remainder, I thought I'd just talk about some more practical aspects of how I go about evaluation and what I think some useful tidbits of information. So hopefully you've worked out where your results are when you've run the model. Is that, yeah, everyone's found the results. Took me a long time. In previous versions of the model, it was much more obvious that the results went in an output directory. Now it seems like there's sort of layers upon layers, and it's like Inception. You have to go within the model to see the results. I think a thing to make you aware of, there are thousands of years of model results available for you to kind of get your hands dirty with, and start to evaluate and start to look at on the Met Office Mass archive. So you will need access to things like Monsoon or Jasmine, and you will also need a Met Office partner to give you access to things like Mass. But it's an incredibly great resource, and I think it's really worth knowing that you don't have to do a 1,000-year run now just to see what the model does. There are 1,000-year runs available for you to look at. CMS do a fantastic job with providing tutorials about interacting with Met Office file structures and data, things like Mass as well. The main thing that you need once you get access to Mass is a bit of a knowledge of the Moose software, which is basically used to interface with the Mass database. And simple commands can be used to list all of the archived files in an experiment. So this is from version 7.3 of the model. You'll be more familiar with the U- string of model identifiers. There's a link here about getting initial access to data, which I think it's really worth having a look at. And so then sort of practical steps how to play with model data. You've been using XConv probably in the tutorials. You can get XConv working for your Mac. There's a Mac binary that works really quite nicely. I think it works for Linux as well. I don't know about Windows. And I think it's great. You can load PP files. I think the nicest thing about XConv is that you can convert PP files to netcdf, because whilst it's great that you can kind of visualize your data and you can do some really nice transformations like zonal means at the click of a button, the automatic scaling kind of and the fact that you can't convert things from kilograms per kilogram into ppb always means it's a bit of a head scratcher in terms of really doing any evaluation. So XConv is great to see, does the data look something like it should? But I I don't think anyone really would use it to do model evaluation. Panoply, is anyone a Panoply fan? Yeah, couple. It's much nicer than XConv. For a start, you can get rid of the horrible color scales and use some nicer color scales. You can actually make good publication quality figures in Panoply. So if you just want to plot data that you have in NetCDF format or GRIB format or even HDF, then Panoply is your friend. I think it's Java-based, I'm not sure, but it runs on most operating systems. NCView, does anyone like NCView? I hate NCView. I don't know why you like it. I mean, it's the nicest thing about NCView is it works. You know, it never seems to have a problem loading files, and you know, making some sort of plot is fine. So it seems like it's really good on memory. You can install NCView through Brewer on a Mac, and if you don't know about Brewer, just Google Homebrew Mac, and you'll find lots of ways of getting the scientific software that you want without having to do too much heavy lifting. But so there are lots of tools out there for kind of visualizing in a point-and-click style. You saw that things like R and Python, which I'm sure you guys love, you can also do quite a lot with. And so as part of the preparation for this tutorial, Luke has been spending some time getting our UKCA evaluation suite to run on Archer. And this isn't sort of something that's formally covered in the program, right, or the tutorial.
I've given an earlier version of that website, but it's not. It wasn't planned on the original.
And so it's just to make you aware of this, so you can either see the web link here for the description of what's going, or you also have the sort of the text printed out in your slides. Basically, the UKCA evaluation suite is, I think, is due for a lot more effort to make it more quantitative. At the moment, it provides a traceable framework for us to look at the performance of the model against observations during the calibration stage, so the model development stage. It's not set up at the moment to do model validation, and that is something that you would need to kind of do yourself. It does compare UKC output to a bunch of stratospheric and tropospheric observations, and there are instructions of how to run it on Archer. So one of the problems with, it's not a problem actually, one of the features of the UKCA evaluation suite is that it will convert the native PP file output to NetCDF file to then do the analysis on. And to do that, it uses Iris. So who's an Iris fan here? Okay, there are some. That's good to know. And the feature is that Iris takes a long time to convert PP files to NetCDF files. So, you know, this isn't sort of long as in, you know, make a cup of tea. This is probably long as in go to the gym, cook dinner, and maybe, you know, have a shower or two, and then come back and then put the kettle on, and then wait for your data to be processed. But then after you've processed the PP files to NetCDF, it kind of chows through in, I think, on the order of 10 or 20 minutes, the scripts, and then spits out a bunch of lovely plots. And so we have plots like this one, which is comparing the age of air in the model. So the model has a diagnostic, which is plotted here in red, and it compares this diagnostic against satellite SF6 data which have been processed to quantify the mean age of air as a function of latitude and altitude. And so you can see that at 50 hectopascals, UKCA really quite nicely sort of reproduces this mean age, and so there's some big uncertainty. Look at those error bars on the observations, and there's no error bars on the model, but it kind of goes through that mean quite well. The evaluation suite also then compares other dynamical prognostic variables. So we have temperature on the left compared to ECMWF era interim, and humidity Q on the right. And so on the left-hand plot we have the absolute bias, and in the right-hand plot we have the relative percentage error. And you can see that in this version of the model, which was at 7.3, there was an overall negative mean bias in temperature, a small mean bias, but that there were some large positive biases and large negative biases. And of particular sort of concern was this warm tropical tropopause temperature bias. And this warm tropical tropopause temperature bias basically allows water vapor to enter into the stratosphere and then effectively creates this huge water vapor bias in the stratosphere. And so then water vapor bias then impacts on ozone and impacts on radiation, and there's this horrible feedback. And you'll be pleased to know that these biases have been the subject of a process evaluation group and have now been sort of removed from the model. Tropospheric ozone column, we can compare to the Bodeca data set, which is a merger of 3 different satellite products and balloon sondes, and effectively, I think those are the black lines here, those contours, and then the colours are the model. And you can see that at this version of the model, the total ozone column agrees quite nicely. We have an ozone hole which extends too long, and so we might want to then understand what are the processes which are contributing to this extension of the ozone hole. So the colours kind of extend down to November and December. We can then look at things like scatter plots as a function of latitude for the total, so this is the mixing ratio. And you see that we've got a good correlation between observations. So I think that's MLS, satellite observations. And we've got a very small standard error. And you can look at polar projections as well and look at how the model sort of spatially captures the total column. For tropospheric ozone, again, there are satellite data sets that we can use to look at the performance of the model, and we kind of consistently see that the peak is shifted in time in the model to July, whereas in observations it seems to peak a bit earlier in June, but that the model has at times had a very good agreement with estimates of the tropospheric ozone burden, and we can start to understand the processes which control tropospheric ozone, so the production, loss, transport of ozone from the stratosphere to the troposphere, and we can calculate these metrics and compare those against literature, and we have a good comparison against literature for a number of those diagnostics. And we can also look at surface observations, and so here we've got the mean bias error and the correlation coefficient for these surface observations, which reveal that there's a seasonal bias in ozone, and that the model doesn't capture the springtime peak in ozone, and this is in Japan, and so that's probably related to some sort of process which we've not yet fully evaluated. Final 2 slides, almost there. Towards process evaluation, so there's a really nice activity that was kind of led by Veronica Eyring and the Spark CCM Val community to do process-based model evaluation. And I think one of the really nice things was the development of a metric to grade model performance. And so once you determine which diagnostics you are comparing or prognostics you're comparing in model and observations, you can grade the performance of that diagnostic by looking at the mean of the model minus the mean of the observations, so the absolute value of that divided by the standard deviation of the observations of that metric or of that diagnostic or prognostic quantity times a third, and then do 1 minus the result of that calculation. And so Steve Hardiman has done a really nice job of that for the evaluation of the UKCA model for the CCMI simulations. And these are the parameters or the diagnostics that he's looked at. And he split this quite nicely into diagnostics which are telling us about mean climate and those which are telling us about variability. And so some of these are constructed by statistical analysis. So we have the amplitude of the leading mode of variability, the EOF, of the 50 hectopascal zonal mean zonal wind for the northern hemisphere, north of 45 degrees. And then some of them are probably more simple measures, the upwelling mass flux at 10 hectopascals. And so what Steve's done, so this paper's in GMD and you can kind of read it for more details. And what's done in the CCM Val community as well is to list all of the model evaluation measures that you have, so this sudden stratospheric warmings, QBO, etc., versus the model simulations. So in this case, we're looking at 7 different model simulations, and they're listed here in these simulations. And then they're graded on a scale of 0 to 1. So the darker colors are telling us that these models perform well for these measures, and the lighter colors telling us that the model isn't performing so well. And so you can see that for something like QBO, the RefC2 model is performing much worse in the QBO than the RefC1. And we can start to then understand what is it about the RefC2 model setup that means that this measure is not so well captured. And I think again, if you have multiple measures that you're evaluating, putting them in some sort of format like this just really simplifies the way that you go about that model evaluation process, particularly at that calibration stage when you're still developing your model. It allows you to say, okay, well, these are the key areas of weakness that we need to focus on. We need to understand a bit more about what's going on at 70 hectopascals, because clearly we've never had a model that captures that upwelling mass flux well, and what are the processes which could contribute to that. So that's it. We've got 5 minutes where we could talk about our favourite tracks on the Nickelback album, if you wanted. Or we could break early and have a coffee, if that sounds good. Thank you very much for listening, and I hope this has been useful. I think there are useful links and papers in these slides, and just enjoy model evaluation. Thank you.
Thanks, Alex. Are there any questions before we continue? Scott?
Well, I mean, it's, I guess, slightly a bit of a tricky one.
Go for it.
But I mean, you started with sort of saying the most important thing in the question, and then you introduced this whole load of diagnostics and metrics. I just wanted to sort of bring it back in a circle, so take one of those questions. How would you go about thinking what would be the best of those metrics that you've introduced? So pick, I don't know, atmospheric budget or something, or aerosol cloud interactions.
Yeah.
What would your process be like? What are the most important valuations that you've introduced? Going back, what might be less useful?
Yep, so that is a tricky question because I don't know anything about any of these.
Okay.
But let's focus on the
Which one do you know most about?
let's do the one I know least about, because then I've caveated any wrong answer. So aerosol cloud interactions. So to me, measures like mean bias probably aren't the right metrics to quantify a process like that. I don't know what would be my go-to approach with that. I think certainly probably for a start I would look at the skill in the model in reproducing clouds, because I mean that's an important starting point. I think I would try and pick apart the timescale that these processes operate under, and so that cloud lifetime sort of timescale. But I don't know what the observations are like there. You know, this isn't my field. And I don't know whether actually you're limited to aircraft data and having to fly in and out of sort of clouds and such. For the oxidizing capacity thing, I think actually the interhemispheric gradient, so the bias in the interhemispheric gradient of things like the methyl chloroform lifetime, which you can calculate and you can observe, would be a key metric I would look at for oxidative capacity and changes in oxidative capacity, because to me that would be telling me about that the process which is controlling the lifetime of methane is OH reacting with methane, and how that OH field is changing latitudinally with time, I think would be well captured with something like a bias between the model and the observations as a function of time. Yeah. But yeah, I mean, a crucially important question, and one I think that really depends on the application, on the objective of what you're trying to do. Yeah. And there, you know, I think the bottom line is there is no one statistic fits all. There's no this is the right way to do model evaluation for everything. I think. I mean, yeah, I think there's a lot of head nodding. There's a lot of thirsty people. There's a lot of tired people. There's a lot of people ready to get stuck into more UKCA and conquer Stash, I'm sure. No, just get coffee. Okay.
Any other questions? No? Well, then that ends the lectures for the workshop. We've got one more practical session this afternoon. I'll also go over the claim forms and things at the start of that session. But let's thank Alex and all our speakers again.